Okay, so today we're going to go ahead and go through the AP Physics C Mechanics pre-response question from 2023. And we're going to go over, I'm going to make a separate video for the first one, second, and third pre-response problem. So what I encourage you to do is go ahead and download these problems from the College Board website, try them yourself, and then check back in on the video. Okay, so after you've done that, you can go ahead and we'll go through and kind of grade them and see how College Board scores them. So, okay, we got this problem, number one, that just gives us an explanation. So now let's go ahead and look at part A. So part A asks us to draw a free body diagram. So comparing spring P and Q. So for both of them, they will have the same normal force and same force of gravity. So make sure normal force and gravity are the same magnitude and size for each one. There's no acceleration in the y direction. And they both have a spring force, so they're both compressed. So it looks like they're compressed this way. So the spring force is going to push back to the left. Now let's go ahead and compare the size of the spring forces. So they are compressed a distance of 0.01 meters. So on our graph, 0.01 is right here. So that looks like 1 Newton for spring P, and then it will be 2 newtons for spring Q. The spring Q, the spring force, needs to be twice as long as it is for spring P. Okay. Oh, sorry, I called it F. It is FS. Okay. Okay. So how the scoring works for this problem is it is just out of 2 points, and you get 1 point for correctly drawing FN and FN and FG on both free body diagrams, and they're at the same magnitude and size. And then you get 1 point for correctly drawing the spring forces and indicating that spring Q is twice as long as spring FS from spring Q is twice as long as the spring force from spring P. Okay, so for part I, so what could be used to estimate the work done on each block? Well, we know work is going to be the integral of f dx, and in the graph above, we are given force and position. So we will just need to find the integral of that graph, or the area under the curve. And this one is just worth 1 point from College Board for correctly answering. Okay, so let's go ahead and look back at these graphs. So we're comparing it equal to the 0.04 mark. Meters. So let's go ahead and look at this graph. So when I look at the graph, the area under the graph for spring P is going to be less than that for spring Q. Let's go ahead and write that. Okay, so spring Q has a greater area under the curve at 0.04 meters than spring P. So this means there is more energy stored in spring P. So if there is more energy stored in spring P, then the block can reach a greater height than that in Q. So it is going to be farther down the line from 0.04 meters for when the two energies are equal. Okay, and this is worth 2 points from College Board. 1 point for indicating that it is greater than, and the attempt at a correct explanation. And then it is 1 point for a correct explanation. So this one is worth 2 points. Okay, so let's go ahead and look at this one. So we know, so we're comparing the max height compared to where the springs are starting. So anytime things are changing heights, velocities, conservation of energy is a great idea. So we know the spring will initially start with spring potential energy for the object, and all of that will be converted to gravitational potential energy. We know gravitational potential energy is going to be mgh. Spring potential energy is just going to be due to how much work each spring puts in, so work dx. So let's go ahead and compare the works done by each spring. So work for P, and it looks like this is, just going back, this is a direct correspondence between this and this right here. So work from spring P is just going to be 1/2 kx squared. Let's just double check that. Yep, because this is a linear spring and K is 100. So let's go ahead. So this is going to be 1/2 100 x squared. So this is going to be 50x squared. For the other spring, work of Q is going to be the integral of f dx. And let's go ahead and look up what f is again. So they tell us f is c k to the 1/2, where c is 20. So that is going to be the integral of 20x to the 1/2. So if we go ahead and integrate that, that will be what? 40/3 x to the 3/2. Yep. Okay. So spring P, since it has x squared compared to spring Q, which is x to the 3/2, this is going to have a steeper, this is like a steeper quadratic than compared to the function below for spring Q. Spring Q, however, initially has more energy in it based on these graphs, because it has this little extra area up here. So until a little ways after 0.04, I think I did the calculation, it was around 0.07 was when the areas will be equal. So Q will be bigger at first. So let's go ahead and just draw P. So let me just draw a quadratic. So this is going to be, P is going to be something like this. And Q is going to start bigger, but then it is going to go, let's see if I can draw that. Oopsies. Okay, so again, P is going to be steeper overall than Q because of the x squared compared to the x to the 3/2. However, Q will initially have more potential energy than P. So for the scoring for this one, you get 1 point for drawing a smooth concave up curve for both of them. So my Q is a little sloppy on the computer. You can do better than that. And you get 1 point for showing that the curves intersect sometime after 0.05 meters and before 0.1 meter. And the last point is to show that Q is above P before the intersection, and then vice versa after the intersection. Cool. So total for this one is going to be 3 points. Okay, so let's look at this next part. So we need the velocity of the two-block system immediately after the collision between blocks A and B. Okay, so anytime there's a collision, I know I'm going to be using momentum conservation. Let me go ahead and draw block A where this collision occurs. So A is going to have some velocity here, and then afterwards they are going to move off together, A and B, and this is, I'm going to say, velocity of both. Because it does say that the blocks stick together. So this is going to be a perfectly inelastic collision. Okay, so first we're going to need to find the velocity of A at the bottom of this ramp. So anytime things are changing positions, changing velocities, I love to use energy conservation. So UG is going to be equal to KE for block A. So block A, so it's going to be mgh equals 1/2 mv squared. So I'll go ahead and simplify this. So then velocity equals square root of 2gh. I'll go ahead and put in numbers. G is 10. The height is 0.75. And I get the velocity to be about 3.87 meters per second. Okay, so now let's go ahead, since we know there's a collision right at the bottom, let's use our momentum conservation. Okay, so again, I drew my before and after picture up there. So momentum of A plus momentum of B equals momentum of both after. So it's going to be mass of A times velocity of A plus mass of B times velocity of B equals mass of both times velocity of both. Okay, so mass of A is 0.2 times, we just found the velocity of A to be 3.87 plus mass of B is, what is that, 0.7 times, it is initially at rest, so just 0. Afterwards, they are together, so what is this going to be, 0.19 when you add their two masses together, and we want to find B both. And when I solve for this, I get B both to be 2.45 meters per second. Okay, so this is just worth 2 points for College Board total. So this part right here, using conservation of energy to find the velocity of A at the bottom, is 1 point. And then for correctly using momentum conservation to find the velocity of both afterwards, it's going to be 1 point. And that includes plugging in 3.87 or whatever you got for velocity of A. Okay, so now we want to find the max compression of the spring when they go off together. So A and B together hit spring Q. Okay, so anytime changing positions, changing velocities, I'm going to use energy conservation. So KE is going to be equal to spring energy. So we know KE is going to be 1/2 mass of both times velocity of both equals, okay, let's see what the spring energy is of Q. So again, for Q, where is spring Q? Okay, there we go. So it is 20x to the 1/2. So this is Q, it is 20x to the 1/2. So we are going to need to integrate this to give us our spring force, spring energy. So this is what, 20x to the 1/2. So when we integrate this, it is going to be, let's see, 40 over 3x to the 3/2. Yep, that's right. So now we got 40 over 3x to the 3/2. So now let's go ahead and put things in. So we know the mass of both was 0.19 together. The velocity was, oopsies, and KE is 1/2 mv both squared. Don't forget that. 3.87 squared we found to, nope, that's simply a mistake. Velocity of both we found is going to be 2.45, not just the velocity of A, equals 40 over 3x to the 3/2. Okay, when I went ahead and did some simplifying, I got x to be 0.12 meters. Okay, so this is worth 3 points total. So 1 point for using conservation of energy correctly. Another point for correctly integrating to find the spring potential energy equation. And then one last point for substituting in what you got from part 1, so 2.45 or whatever you got from part 1, so your velocity for both of them into the equation, and then solving for x from there. Okay, so they're telling us in this one the max compression of spring R is greater than the max compression of spring Q. So let's go ahead and compare like the spring energy equation. So for spring Q, we know that is going to be essentially 2/3 upon integrating cx to the 3/2. And for R, spring energy is going to be 2/3 dx to the 3/2. Okay, we know those have to be equal because of, conservation of energy, comparing the same. So, okay, let's see. So the max compression of R, so this is greater, so this is smaller. The 2/3 are the same in each case. So then for it to all even out, D has to be smaller and C has to be bigger. So for scoring for this, you get 1 point for checking the correct box, and then 1 point for a correct explanation using ideas of conservation of energy, and then comparing the spring energies before and after. Or sorry, comparing the spring energies after of Q and R, since they will both start with the same total energy. Okay, so now we can go ahead and add up how many points you got. My general rule of thumb is that if you are getting around 9 to 15 total points, your AP score is going to be about a 5. If you're getting around 7 to 8 points, about a 4. Around 5 to 6 points is a 3. Around 4 points total, a 2. And then 0 to 3 total points is around a 1. And that's just my rough estimate of AP score conversion. Thanks for watching, and let me know if you have any questions.